The rotational motion lab is a rotational form of Newton's second law. Newton's second law, of course, is the vector sum of the forces equals mass times the acceleration. And we have to use, it's a little more complicated, the form that we use for rotational motion is torque. That's capital tau, Greek tau. And instead of mass, which we also have to talk about, we use moment of inertia. Instead of, since that's a Greek tau, this is a Greek a, and we have a alpha for angular acceleration. So torques cause objects with the moment of inertia to have angular acceleration. That's the rotational form of Newton's second law. So we got to figure out a couple things about all these things. That is, torque is a little more complicated than force. Moment of inertia is a little more complicated than mass. And angular acceleration is just a little more complicated than regular acceleration, linear acceleration. So let's talk about these quantities. So torque, is, again, the Greek symbol tau we use for torque. And it's actually, it's the product of a force and where you apply it relative to the axis of rotation. All the things we're going to talk about in this course are going to be rotation about a fixed axis, an axle, so to speak. So we're going to have something that's rotating. One thing we're going to have is a disk rotating about an axle. The axis is coming straight out of the board, and it's going to be rotating. Now, if we apply a force to this, I think you can see that if I apply a force here, let's say a 1 Newton force, this is going to rotate this way. And if I apply the same 1 Newton force over here, it's going to rotate the other way. And you can probably also see that if you apply a 1 Newton force here instead of here, that I'm sure you get the feeling for the fact that this force applied here is going to have a bigger rotational effect than this same force applied closer to the axis of rotation. Okay, so let me define torque. Torque is defined as the perpendicular distance from the axis of rotation to where you apply the force. This is called a line of the force. So this would be the line of this force. This would be the line of this force. So our perpendicular here is this value, and our perpendicular here is this value. Obviously, this value is bigger than that. Therefore, the same force applied at a bigger distance away from the axis of rotation gives you more torque. So it's more complicated. And I don't know if you've gotten to that in your class or not, but that's what our perpendicular means, times the force you apply, say 1 Newton force. That's roughly the force we're going to apply. We have, and you probably remember this from earlier experiments, we're going to have 100 grams, which is 0.1 kilograms. And if I multiply that by 9.8 meters per second squared, I'm going to get approximately, well, 0.98, approximately 1 Newton, 1 kilogram meter per second squared. So 100 gram mass is 1 Newton, basically, almost exactly. 0.98 newtons to be a little more specific. So we're going to apply a 1 Newton force to this rotatable object. So the object we're going to rotate is, let me try to draw a sort of three-dimensional sketch of it. It's a big plastic disc that has a mass of something like 900 grams, 0.9 kilograms. And on top of that disc, there is, and I'll draw that over here, there is a triple stack of pulleys. And this is the side view of a pulley. There's another pulley on top of it, and there's another pulley on top of it. Okay, this pulley here has a 2 centimeter radius. That's the pulley we're going to use. You'll see when we look at the equipment that I've got it set up so that if you're careful, the string that you're going to apply a mass weight to is going to roll up on the second pulley automatically. And you might double check to make sure that's happening. So we're going to wind up our string on this second pulley, the 2 centimeter pulley. Now the mass that we're going to use is a 100-gram mass on the 5-gram platform. And if you want to, you can check the mass of it. It's probably pretty close to 105 grams. So 0.105 kilograms, that's 105 grams, right? Times 9.8 meters per second squared, that's mass, times acceleration. The acceleration due to gravity, that's going to give you weight. We're using our little platform with the masses with the holes in them, the brass masses. We'll put a 100-gram mass on the 5-gram platform, which makes it 105 grams, which is 0.015 kilograms, multiplied by the acceleration due to gravity. Since we're turning that force, that's the force of weight, is 1.029 newtons. So the torque then that's being applied at the distance of 2 centimeters from the axis of rotation is 1.029 newtons times 0.02 meters, which is about 2.0206 Newton meters, rounded off the 3 decimal places. 0.2058, 0.0206 Newton meters. So this is the torque we're always going to be applying to everything we test in this experiment. So that is our theoretical torque, but of course we can't get away without friction, so we have some friction. So that's going to reduce the torque because it always acts against the forces that you want to apply. We learned that from our inclined plane lab. And so this is going to be a little less than this. So we need to find out what the really true torque is. That's kind of the optimum value if there were no friction. We have friction in the bearings on this big disc, which is fairly heavy, almost a kilogram, and we have friction on in the smart pulley that we're using to figure the acceleration. And again, just like we did before, we're going to plot velocity versus time, and we're going to get the slope of that, which is acceleration. By the way, that's linear acceleration, which is A, not alpha. So the graph will give you the linear acceleration of the weight that's slowly falling to the floor. It's not a freely falling object, but it's a falling object. So it's going to be a fairly slow acceleration, fairly low acceleration, because we have a pretty massive disk to rotate, and we have not a very big mass and not a very big distance, so we have not a very big torque to cause it to rotate, to accelerate in an angular way, and so we're going to get a pretty small acceleration, way, way less than 9.8 meters per second squared, of course. So from the velocity, this is linear velocity of the falling mass versus time. We're going to get, the computer will take data points, probably a couple, 300 data points over a period of a couple seconds as the mass falls down, and you're going to be able to get the slope. And again, we need to do this 3 times to get an average and to see what variation there is in the values. So don't bother double-clicking on the box and getting the uncertainty here. We want to get the uncertainty between different runs, not the uncertainty in one particular run. So we'll get those numbers and average them and find out the maximum deviation. That's going to be probably your largest error source. So make sure you get that. So we're going to run this experiment 3 times for each configuration of an object rotating on that axis and average those, get the maximum deviation. That's your biggest error source. So that's a clue for your error analysis. Other errors are weighing errors, masses, and so forth, and those are pretty minimal if you use the balance. And again, if you want to double check your 105 gram mass and make sure it's real close to 105 grams, feel free to do that before you connect it. Okay, so as I say, torque is a little more complicated than force. Now we know what torque is. How do we get angular acceleration? Again, angular acceleration is linear acceleration, which is the slope of the graph you're going to get, which is the linear acceleration of the mass that's falling down to the floor, divided by r, the radius. Okay, so what radius? Well, your string is wrapped around a pulley with a 2 centimeter radius. So that is the radius you put in there. So whatever this is, let's just say this acceleration is 1 meter per second squared. That's way too high. It's just 1 meter per second squared. And so this is the radius, 0.02 meters. So that's going to be 50 radians per second squared. Radians, I think you've talked about radians now with rotational motion. Radians are the corresponding rotational unit. Instead of meters, we use radians. Just in case you haven't got to that yet, 1 radian is about 57 degrees. There's the circumference of a circle is 2 pi r, right? So if circumference is the distance, this distance around, so if we divide the distance around, which is the circumference, by 2 pi, we get the radian measurement. So 2 pi is about 6. There's 360 degrees in a circle. If you divide by a number that's a little over 6, you're going to get a number that's a little under 360 divided by 6, which is 57.3 degrees, if you want to be a little more exact. So 1 radian is 57.3 degrees. That's a conversion factor from degrees to radians, or from revolutions to radians. There's 2 pi radians in 1 revolution. It's another conversion factor. And we talked about that when we did the centripetal acceleration experiment. Remember, we had to convert from revolutions per second to meters per second for speed, and that involved this 2 pi business. 2 pi r is a circumference in which something travels in 1 circle. Okay, so that's 1 radian. Lots of conversions there, so please, you're going to get totally mixed up if you don't stick with SI units right away. Convert your centimeters to meters right away. Convert your grams to kilograms right away. And then you'll be okay. So the moment of inertia of a thick ring is, here's our thick ring. Again, it has an inner radius, r sub I, an outer radius, r sub O. And if that ring were a theoretical thin ring, where all the mass was concentrated at the same distance from the axis of rotation here, that would be the average radius, which again would be along this dashed line. So our average, of course, our average is r inner plus r outer divided by 2. Just like the case of a mass at the end of a string, the radius r, mass here rotating around in this big circle around this axis of rotation, since all the mass is concentrated at the same maximum distance r away, the moment of inertia here is m r squared. If you replace a ring with a mass that's also all located at the maximum distance r, so all the mass at the ring is going to be at that same distance r. That's actually then that average distance. So the moment of inertia of a thick ring, a thin ring, which we're modeling with the thicker ring, is simply the mass of the ring times r average squared. That's the moment of inertia you use for the thick ring. So we need to measure the average radius of the ring. So your angular accelerations are going to be a lot bigger than your linear accelerations because you're dividing by 0.02. So they're going to be 50 times bigger. Okay, so we have alpha figured out, we have torque figured out, and we have moment of inertia figured out. Right? So the moment of inertia of the disk by itself, the mass of the disk, we'll call m sub d, and this is the radius of the disk, we'll call it big R. That's something like 13 centimeters, converted to meters, of course. And so we can figure out the moment of inertia of this disk is 1/2 m times of the disk times r squared. So that's the moment of inertia of the disk. You can measure that, figure this out. It's a fairly small number because this mass is in kilograms, and the disk is less than a kilogram, and the radius is in meters, and 13 centimeters is a lot less than a meter. So you're going to get a pretty small number, like 0.00 something, for this answer. And the units are meter times meter squares times kilogram. Kilogram meter squares. Those are the units for one last object we're going to put on top of the disk is an equilateral triangle, and these are homemade equilateral triangles out of a piece of 2x4. And so we've got the hole drilled again at the center of mass of the equilateral triangle, which is a third of the way up from along this perpendicular bisector to here. So you put the triangle on top of the disk. That's even worse. You put the triangle on top of the disk at its center of mass, and you rotate them together, and you know the story. The torque, which is always the same, as the actual torque is equal to excuse me, the moment of inertia of the disk plus the moment of inertia of the triangle times alpha, which you measure by the slope of the velocity versus time graph. That gives you A. A divided by R gives you alpha. So measure this, measure each side, because I'm not guaranteeing this is a perfect triangle. Measure each side, take the average value for the sides, and then apply that to the calculations. The inertia of a triangle is equal to 1/12 mass times the length of a side squared. Again, you plug that into solving for this, you know that, you know that. Solve for the moment of inertia of the triangle. So 3 things to rotate on top of the disk, which you are assuming you've calculated correctly the moment of inertia of. Parallel axis theorem again. I sub p is equal to I center of mass plus md squared. Now, the center of mass here contains all the objects as though they were rotating about their center of mass, which means it's the disk plus the 2 cylinders, as though they were rotating about their center of mass. So this would be 1/2 mass of the disk times the radius of the disk squared, plus, again, these are basically a cylinder and a disk are the same, so it would be 1/2 mass 1 plus mass 2. These masses are labeled A1 and A2, or B1 and B2, And so that's what I mean by these two masses added together, 1/2 m times the radius of the cylinder squared. This is the moment of inertia of the cylinder about its own center of mass, which is that small number I talked about earlier. So this whole thing is the moment of inertia of all three objects, the two little cylinders and the big disk, as though they were all rotating about their centers of mass, which of course the disk is, but these are not. So this is going to be the term that's going to give us the correct value. So we experimentally, the usual way that we've done everything, we're going to get the moment of inertia of everything. We're going to get I sub p experimentally. Then we're going to calculate also using the moment of inertia of the disk about its axis of rotation and the moments of inertia of the two cylinders as though they were rotating about their axis of rotation. That's all this thing here, plus md squared, where d is the distance on the disk from the little positioning holes where the little cylinders are sitting. So this is d. This is the distance from the axis of rotation to the parallel axis of rotation of each cylinder. So that's what goes in over here, and this mass is the mass of the two cylinders together, about 800 grams. Okay, it's a little complicated, but again, this is the moment of inertia of everything that's rotating theoretically about its own center of mass axis, which the disk is rotating about its center of mass, but these little things are not, so we have to calculate their moments of inertia. Again, this is almost a trivial, almost an ignorable term. You might see how much smaller that is. It's maybe 50 or 100 times smaller than this, so we can just almost forget about that. But that number gets very big when the distance is the distance from the axis of rotation to the parallel axis of rotation, which is why this term will become significant. So we want to compare this calculated moment of inertia of this whole business rotating about, these things rotating about an axis parallel to their center of mass, to the actual experimental value we get in the usual way by just finding alpha and so forth. All right, so here's the setup. I've got the string wrapped around the second pulley. Will wrap up automatically, if you're careful, on the second pulley. We've got it set up at the right height so that it does that automatically. Make sure it doesn't bump into this. It's not swinging enough to bump into that little knob, so it should be fairly calm before you let go. This is 105 grams, and so we're ready to do this. You want to make sure that when the string comes off the pulley, there's no kink in the direction of the string, and so you might have to move this back and forth a little bit until you see that the string's coming right off the pulley and there's no angle here. So that adds to the torque on that pulley, and also couldn't make it fly off the groove, which isn't very deep. Okay, so it's a very simple experiment. You're going to only have to do this 12 times for the whole period, and so we need to get 3 runs of each of 4 different situations with the bar and the ring and the triangle, and then the 2 added masses with the parallel axis there. So all you have to do is start it and let it go. So it automatically wraps up on the wrong side of the pulley, so you're going to have to rewrap it to do the next run so that we don't have this coming off at an angle from the pulley. So we're ready. That's one. Okay, so we're going to Logger Pro and use our favorite probe so far, which is the Smart Pulley. Go to File, Open, scroll down till you get Probes and Sensors. Double click on that, scroll down till you get Photo Gates, double click on that, and then scroll down till you find the pulley. There it is. double click on that. Okay, so that will bring up the screen, and again, if you push the connect button, that will turn the connect button up here green, which means you're hooked up, you're ready to go. I would recommend, first of all, since we only want the velocity versus time curve, which you're pretty much getting used to by now, I think, so we want to just get rid of the distance versus time curve and the acceleration versus time curve, and maybe expand this to fill up the whole screen. I'll get it eventually. Okay, again, it's already labeled nicely, velocity versus time, that's what you need. And let's just go ahead and do one run and see how it goes. So you don't have to coordinate your start. Your partner can be ready to release it. All you have to do is hit the collect button, and then your partner can release it. Okay, well, here's where it hit the floor, or here's what it ran out of string. And so if you hit the auto scale button, which you should, you get a nice graph here with a little bit of a bump in it, which is a little puzzling, but we certainly don't want this stuff. We just want, now it's your call whether you want to only analyze this part that looks really nice and linear, or you want to analyze the whole business and hope that that's still pretty linear up to here, maybe. It's your call. You might try it both ways and see how much difference it really makes. Okay, so I'm going to analyze the whole business. The linear fit will give me the slope, which is 0.02842 meters per second squared. You don't need to double click on this box to get the uncertainty in the slope necessarily, because the big uncertainty, as it did before in the free fall experiment, the big uncertainty is the variation in the number that you get from the slope for the different runs. That's where you get your error in the value for the acceleration. So this is linear acceleration. You need to average the 3 runs linear acceleration, then find the maximum deviation in those values, and that's the error in your acceleration term, which is probably the biggest single error in the experiment. The other error would be mass, but if you mass everything on the balance, as you already know, that reduces that error to insignificant value. So that's how we do the experiment. Again, you've got 4 parts of the experiment, and the job is to calculate the moment of inertia of those 4 things that are on top of the disk, assuming you know the moment of inertia of the disk, and the torque, and the angular acceleration. That's linear acceleration. Angular acceleration is this number divided by 0.02, which is the radius that the string is wrapped around, giving you the torque. Okay, that's it.